In this lecture video, we continue looking at conditional distributions and their characteristics, and we're going to get into example 52, which deals with continuous random variables. So let x and y be continuous random variables with joint PDF given by this expression here, which we've seen in a couple other examples. We've dealt with this distribution before. So we want to find the PDF and the CDF of the conditional distribution of x given y. We also want to find the mean, the variance of the conditional distribution of x given y. And then we also want to find the PDF and the CDF of the conditional distribution of y given x, and then find the mean and the variance of the conditional distribution of y given x. And so let's proceed to see how we do this. And so first we'll find the conditional PDF of x given y. So denote the conditional PDF of x given y in the usual way. F in the subscript, we've got 1 given 2, and this corresponds to the first variable, conditional or given the second. Now, since for a given value of y in the unit interval from 0 to 1, the space of the random variable x is the unit interval as well. And so we know that the conditional PDF of x given y is going to be 0 if we evaluate that conditional PDF at any value of x that is not in the sample space of x. Now, for values of x that are in the unit interval, we have to do a little bit of work. All right, and so we're going to appeal to the definition of the conditional PDF of x given y, which says that the conditional PDF of x given y is going to be equal to the joint PDF divided by the marginal PDF of y. Now, for values of x and y that are both in the unit interval, the joint PDF of x and y is 4 times x times y, and for the and the marginal PDF of y evaluates to 2 times y. And so when we solve this, simplify this, we get 2x. And so putting these two results together, the conditional PDF of x given y evaluates to 2 times x as long as x is between 0 and 1, and it's 0 otherwise. Now, I would point out that this is the same as the unconditional PDF of x itself. I'm sorry, well, yeah, and so we can also call that the marginal PDF of x. So the conditional PDF of x given y is equal to the marginal PDF of x. So I just wanted to point that out. So we've actually seen this, we've seen this PDF before, haven't we? Okay, and then to derive the conditional CDF of x given y, we'll denote it first by cap f, given the first variable, or it's a function of the first variable given the second. And since for a given value of y in the unit interval, the space of x, again, is the unit interval, so we know that the conditional CDF of x given y is going to be 0 if we evaluate it at any value of x that is less than or equal to 0. And it's going to be equal to 1 if we evaluate it at any value of x that is greater than or equal to 1. For values of x that are greater than 0 but less than 1, we've got to do a little bit of work here. And so we're to do this, to obtain this, the conditional CDF of x given y, all we have to do is integrate the conditional PDF from 0 up to x. All right, and so we know that over this interval, the conditional PDF evaluates to 2 times the argument. So in this case, because I'm using, because I have x up here as the upper limit of integration, I can't use x as the variable of integration, so I'll just use t. Okay, and so the conditional PDF of x given y over that interval evaluates to 2 times t, which we can then solve this integral, and we get x squared. And so putting these three results together, we get this piecewise defined function, which is the conditional CDF of x given y. Now, similar calculations give the PDF of the conditional distribution of y given x. And so we see that this is what that looks like here. And then the conditional CDF would follow suit. And again, I would point out that in this case, the conditional PDF of y given x is the same as the marginal PDF of y. Okay, so now let's look at example 53. Again, let x and y be continuous random variables with joint PDF given by this expression. And this is similar to the previous example, but remember that the difference is in the sample space, the joint space of x and y. Here, the joint sample space is not the entire unit square, but it is the upper left triangular portion of the unit square. All right, because of this constraint here that x has to be strictly less than y. And so we are to find the PDF and the CDF of the conditional distribution of x given y. Once we've found the conditional PDF, we can find the mean and the variance of the conditional distribution of x given y. All right, and then we want to note how each of these varies as a function of y, if indeed it does. We also want to find the PDF and the CDF of the conditional distribution of y given x. Once we found the conditional PDF of y given x, then we can find the mean and the variance of the conditional distribution of y given x. And again, we want to note how each of these two distributional quantities depends, if at all, on as a function of x. Okay, so let's see how to do this. And so we'll first find the PDF of the conditional distribution of x given y. And so we will denote the conditional PDF in the usual way. And we know that for a given value, and we have to be careful here. We have to be careful here because, remember, we've got this constraint relating x and y. And so for a given value of y in the unit interval, so that y is fixed, we know that x can be no larger than y. And so for a fixed value of y in the unit interval, the space of x is going to be the interval from 0 up to y. Now, having said that, we know then that the conditional PDF of x given y is going to evaluate to 0 for any value of x that is not in the interval from 0 to y. So we get this value kind of for free just based on what we know about PDFs. They're always 0 outside of the space of the variable of interest. Now, for values of x that are between 0 and y, then the conditional PDF of x given y is going to be given by this ratio. Again, this is the definition for the conditional distribution of x given y. And it's going to be the joint PDF of x and y divided by the marginal PDF of y. Now, for this situation, for this example, for this joint distribution of x and y, the joint PDF is equal to 8 times x times y. The marginal PDF of y, which we found in a previous example, is 4 times y cubed. And so when we evaluate this, we get 2x over y cubed. I'm sorry, 2x over y squared. And so the conditional PDF of x given y is going to evaluate to 2 times x over y squared as long as x and y are both in the unit interval and x is strictly less than y. For any other common values of x and y, this conditional PDF evaluates to 0. So fairly straightforward. Once we have the joint PDF and the marginal PDF, it's fairly straightforward, I think you would agree, to find the conditional PDF. All right, now to find the conditional CDF of x given y, we'll denote it in the usual way, cap f, given the first variable, or I'm sorry, cap f which is a function of the first variable x given the second variable y. Now, since for a given value of y in the unit interval, the space of x, again, is the interval from 0 up to y. And so it follows that the conditional CDF of x given y, which remember, the CDF is a probability accumulator. And so if we evaluate that CDF, and I notice that I have a little bit of a typo here. This should be 1 given 2. Let me correct that. Okay, so I corrected that notation. So for a given value of y in the unit interval, we know that the space of x is the interval from 0 up to y. So it follows that this probability accumulator is going to be 0 for any value of x that is less than or equal to 0, and it's going to be 1 for any value of x that is greater than or equal to y. Okay? Now, for values of x and y that are both between 0 and 1, and for which x is strictly less than y, then the conditional CDF of x given y is going to be obtained via integration. We're going to integrate the conditional PDF of x given y from minus infinity up to x, and that simplifies to this integral of from 0 to x of 2u over y squared du. And again, we can't use x here as the variable of integration because it's up here as the upper limit of integration. And so anyway, when we put these three results together, we get the conditional CDF of x given y. And now I would point out here that again, this is the formula, this piecewise defined function for the conditional CDF of x given y. And you note that this does in fact depend on y. This is a function of y. And so you can see that y shows up down here in the denominator of this expression here, but it also shows up in the interval over which this expression is applicable, and as well it also shows up in this interval here over which this portion of the CDF is applicable. So this does, the CDF, the conditional CDF of x given y does depend on the value of y that we're conditioning on. Now, we want to find the mean and the variance of the conditional distribution of x given y. And we can, it's fairly straightforward to solve or to find a general formula for the kth raw moment of the conditional distribution of x given y. And so we're going to do that and then use this general formula to find the mean and the variance and so forth. All right, so we're finding an expression for the conditional expectation of the kth raw moment, x to the k, given a particular value of y. And the formula for that turns out to be 2 over k plus 2 times y to the kth power, where again k is the particular value, or the exponent, the moment that we want. And so with this, we have the first 4 raw moments for the conditional distribution of x given y. The conditional expectation of x given y, first raw moment, is equal to 2/3 times y. The second conditional raw moment, the expected value of the expectation of x squared, given that that y is equal to x, is 1/2 y squared. The conditional expectation of x cubed, given y, is equal to 2/5 times y cubed, and the expected value of x to the 4th, given that y is equal to y, is 1/3 y to the 4th power. And so using the expansion formulas, we get the formulas for the conditional central moments of x given y. So the second central moment for the conditional distribution of x given y is equal to 1 over 18 times y squared. And so that's the variance of the conditional distribution of x given y. The third central moment of the conditional distribution of x given y is negative 1 over 135 times y cubed. That's the numerator in the skewness coefficient. And then the fourth central moment for the conditional distribution of x given y is equal to 1 over 135 times y to the fourth. And again, that is the numerator for the kurtosis coefficient. And so I have this summary page, which shows not only the mean and the variance of the conditional distribution of x given y, but I've also computed the skewness and the kurtosis coefficients for the conditional distribution of x given y. And so you can see here that although, even though the mean and the variance of the conditional distribution of x given y vary as a function of y, the skewness and the kurtosis are constant as a function of y. Now let's focus on the conditional distribution of y given x. And so we'll denote the conditional PDF of y given x in this way. And since for a given value of x in the unit interval, the space of y ranges from x up to 1, we know that the conditional PDF of y given x is going to be 0 if we evaluate it at any value of y that is not in that interval from x up to 1. Now for y greater than x but strictly less than 1, the conditional PDF of y given x is going to be given by the definition as the ratio of the joint PDF of x and y divided by the marginal PDF of x. And so that's going to be equal to 8 times xy over 4 times x times 1 minus x squared, which when simplified gives us 2 times y over 1 minus x squared. And so this is the formula for the conditional PDF of y given x for values of x and y that are both in the unit interval and for which x is strictly less than y. The conditional PDF of y given x evaluates to 2 times y over 1 minus x squared, and for any other values of x and y, it evaluates to 0. We can go through similar calculations as we did before to find a similar process, let's put it that way, to find the conditional CDF of y given x. And that turns out to be, well, it's 0 if we evaluate it at any value of y that is less than or equal to x. It's equal to 1 if we evaluate it at any value of y greater than or equal to 1. And for values of x and y in the unit square, where x is strictly less than y, the conditional CDF of y given x evaluates to y squared minus x squared over 1 minus x squared. And so putting those three results together, we get this expression for the conditional CDF of y given x. So it's the fully specified expression. It's defined at every real number y. Okay. Now to find the mean and the variance and hopefully the skewness and the kurtosis again, we're going to derive general expressions for the expected value of y to the kth power given x. So the general expressions for the raw moment, the kth raw moment of the conditional distribution of y given x. And so it turns out that the expected value of y to the kth power given x is equal to 2 over k plus 2 times 1 minus x raised to the k plus 2 power all over 1 minus x squared. And so then we can utilize that general formula to very easily then find the first 4 raw moments of the conditional distribution of y given x, and which are given here. And then we can use the expansion formulas to find the second, third, and fourth central moments for the conditional distribution of y given x. Okay, which here we have an expression for the, this would be the variance of the conditional distribution of y given x. All right, the second central moment for the conditional distribution of y given x. Here we have the formula for the third central moment for the conditional distribution of y given x. And then here we have the formula for the fourth central moment for the conditional distribution of y given x. And then utilizing those formulas, we can come up with expressions for the mean, variance, skewness, and kurtosis. And because it's very, let's see here, these are fairly complicated, so at least at this point we're not going to plug those in and try to simplify them because it's very complicated. But obviously we could use these formulas to calculate the particular central moment that we need for a given value of x, and then use these formulas to get the skewness and the kurtosis for the conditional distribution of y given that particular value of x. We could also use these formulas in constructing plots, graphs of those quantities. One thing that we can definitely see here is that both the mean and the variance of the conditional distribution of y given x depends functionally on x. These are not constant as a function of x. Now, it's more difficult to be able to discern that kind of thing for the skewness and the kurtosis of the conditional distribution of y given x because of the complexity of these central moments. So we would have to evaluate these, perhaps plot these using a graphics package, maybe using SAS or R or Minitab or something like that, maybe even a spreadsheet, and just check to see what the skewness and the kurtosis look like as a function of x. Okay, so that is the end of this particular lecture video where we looked at the conditional distributions and characteristics of those distributions involving continuous random variables. And so we're going to continue on in the next lecture video looking at stochastic independence. We'll define that and then look at some results involving stochastic independence and then some examples.